And this jack goes into his primary visual cortex in the back of his head. And again, there's a huge mismatch. There's about several billion neurons in your primary visual cortex, and this data cable has 256 electrodes that it connects to. So you wouldn't think they could possibly work, but it produces what they call limited mobility vision. What does that mean? Well, let me show you what it meant for Jens.
I was able to very carefully drive and look from my left side to my right side, making sure I was between the row of trees on the right and the building on the left. When I got near any obstruction in the front, I would see that there was an obstruction. I would also see the lack of obstructions, and then when I backed up, I would be able to inspect for obstructions there. It was really a nice feeling.
It was really a nice feeling. That's a blind man driving a Mustang convertible. Jens has terrible vision. It's absolutely atrocious. You wouldn't want it, but it's a lot better than zero vision. It's a quantum step up. It's a proof of principle that we can do this, and the tech will get better. Now, I told you the requirements, data input, multiple data types. Okay, we've got audio, video in. What about data out? That's one of the requirements too. Well, we have also had success getting data out of the brain. This is a neuroscientist named Phil Kennedy in Atlanta. He's also a science fiction writer. And this patient here was named Johnny Ray, 53 years old, Vietnam vet, drywall contractor, played blues guitar on the weekends. One day, in perfectly fine health, he had a massive stroke. Just collapsed, woke up in the Veterans Affairs Hospital in Atlanta, paralyzed from the neck down. They'd had to do an emergency tracheotomy to save his life, so he couldn't speak either. So his only way to communicate with the outside world was blinking, once for yes, twice for no. Kennedy had done work in animals, in monkeys, where he could place an electrode inside the motor cortex, the part of the brain responsible for motion, and train a monkey to move a cursor around on a computer screen. He applied to the FDA for permission to do this experiment in humans. They allowed it with a couple caveats, one of which was he couldn't leave any wires going in or out of the skull because they were worried about infection if things would get into the brain. So they made this system wireless. It's a single electrode that goes into the brain, things are sealed up, it has a small wireless transmitter receiver, and it gets its power wirelessly too. So you'd wear a cap on top of his head that did the data and power wirelessly to this thing. Now, this is an even bigger mismatch because it was literally one electrode to millions of neurons. So again, there's no reason you would think naively that would work. But it does. It allowed him to type out on an on-screen keyboard messages to his friends and family, which was a quantum leap up from just being able to blink for yes or no. And this technology has gotten better, and it's in human trials now with more sophisticated systems that have 40 or 80 electrodes. And let me show you a video of one of the more recent experiments or proofs of principle in this area.
You're watching the most advanced brain-machine interface in action. Kathy Hutchinson is paralysed and unable to speak, but just by thinking she's able to control the movements of this robotic arm and drink her morning coffee. She's part of a pioneering study run by researchers at Brown University in the US.
People who are paralyzed have their brain disconnected from their body, so they're not able to.
So, yeah, it is life-changing for her as well. And you notice it's something that she was very motivated to do, which is drink coffee. There's another video of another woman who has a similar system, and they actually asked her, what's the first thing you want to do when you can control this robot arm? And she said, I want to feed myself chocolate. You can go find that one online, and she does a great job. It's like, get the big one. Okay, so we have data into the brain, data out, 3 different data types we talked about now. Another interesting thing that's being done already approved for use in humans, is what they call deep brain stimulators for control of Parkinson's disease. In Parkinson's, normally drugs are effective for a while, but they stop being effective over time. What they found is these deep brain stimulators that stimulate the parts of the region of the brain that produce dopamine, which is the chemical we have a problem with in Parkinson's, have a much longer duration of effectiveness, which is great. But they've also found some side effects, that in some patients that had severe depression before the implantation of these things, their depression is suddenly gone. And in some patients that had severe OCD, their OCD is suddenly gone. So now we're in human studies specifically for the purpose of using these deep brain stimulators to treat previously incurable depression and OCD. And that's, if you think about it, it's sort of the work that Jose Delgado was doing, but in a medical rather than very creepy sort of direction. So that's the work that's happening in humans right now. But what are the future opportunities? This is science fiction that I'm writing after all, so I'm not going to stop right there. Well, there's a lot of things that we can do in the future, potentially, about our higher functions, the way that we think, our memory, our intelligence, the things that really make us human. And there's interesting work happening on this right now in animals. So Guy Pearce in the film Memento played Lenny. If you remember this film, Lenny can't form long-term memories. Lenny only experiences things and then he forgets them within a few minutes. Okay? This is kind of an extreme case, but a few cases that's extreme do exist, and tens of thousands of cases, a little bit less extreme, exist in people who've had damage to a part of their brain called the hippocampus. The hippocampus is part of your brain that's responsible for taking memories, taking experiences, and encoding them for the long term. So researchers right now are working on, can we fix the hippocampus or provide a prosthesis, an artificial hippocampus that takes its place? So we have experiments happening in rats where they take a rat that has damage to part of the hippocampus and they take this hippocampus chip they developed that acts like the neural circuitry in the hippocampus, and they basically put it in with a bypass, which is a big array of electrodes on either side. So the signal goes down the hippocampus, goes to this, comes back, and keeps going. And what they find is that in these rats, who normally would have severe problems with memory, they can restore the rat's ability to learn things and remember things. But they didn't stop there. They've gone on to find that they can improve the rat's memory beyond normal rat learning abilities, and they can selectively choose which memories they want to encode forever, essentially. Because the memories that are encoded on this chip, they can just say, okay, this one's never going to degrade. We're just going to hang on to this, and then if you want, you can play it back to the rat and have the rat have perfect eidetic memory of whatever it is that you want. So you can put a rat in a maze, have the rat learn the maze. Normally, a month later, you put it back in the maze. It might remember it, it might not. But with this chip, you can turn on that memory, and it will remember it perfectly. So you can see the potential applications in humans if this gets that far. And we've also messed with core decision-making, pattern matching, parts of what we call intelligence or IQ. So these monkeys, these are macaques, and a study has been going on in macaques implanting a neural interface in their frontal cortex. So the frontal cortex is what we call the seat of executive function. It is the apex of the pyramid, if you will. So I think it coordinates everything else. It handles attention, working memory, juggling different tasks, all of that. So what they've done in these macaques is they have implanted this brain implant, and they train the macaques on what they call a pick and match test. It's basically a monkey IQ test. And this implant watches and sees what neurons are firing and how they're working when the monkey gets an answer right and when it gets it wrong. Then, after the implant kind of understands how it works, they impair the monkey's performance on this test. They do that by giving them large doses of cocaine. So the monkeys don't complain, they hope they're the experimental group, not the control group, but their performance does go down. Then some of these monkeys, they flip the implant back into an active mode, where it is observing what's happening, and if it sees a pattern that looks like they're going to make the wrong decision, it intervenes and tries to flip it to the right for the decision. And they find that in those monkeys, they can restore test performance back up to where it was. And in fact, they can go higher. The average score on this test for the monkeys that are not impaired but not boosted is 75. In the group that has the implant in the active state, you score an average of 85. So obviously, that leads to the planet of the cyborg apes. But it's very suggestive. Eventually, these technologies will get to human beings. Now, for most of us, the power of computers isn't about solo work. They're not just memory or intelligence. There was a time when computers were word processors or spreadsheets. They were really fancy typewriters or fancy abacuses, essentially. But now, the real way that they enhance our lives, for the most part, is through communication. Right? They're valuable to us because we're sending thoughts and ideas and emotions and pictures, whatever not else, back and forth in a work setting, in a personal setting. And that's where I think this technology really has the most applicability, and that's really how it's depicted in the novel as well, is it's about connecting people in various ways, for good or bad. And we are starting to get there as well. DARPA, who funds advanced research for the DoD, has a keen interest in human enhancement. And they have a specific program called Enhanced Battlefield Communication, which is about how do you give soldiers in the battlefield a better understanding of what's happening in that context, what's happening with the rest of their squad, their superiors, and so on. So DARPA funded this study that happened at Wake Forest. And in this study, there are 2 rhesus monkeys in separate rooms, soundproofing between them. And they're connected via implants in their auditory cortices, so the part of the brain responsible for hearing. And so the connection goes from one monkey's auditory cortex to a computer to the other. And then what they do is they play a sound for monkey 1, and as they hoped, monkey 2 can hear that sound and can identify it. They know what it is. So that's a communication 2-way of audio, and they're hoping that this means that you can have soldiers who are just innately wired to their squad and know exactly what's going on. We've also done this with video. We have gotten video out of the human brain in a couple ways. This particular one I'm going to show you is non-invasive. I mean, there's no electrodes. They just put someone in an fMRI machine, a brain scanner, which gives them a disadvantage. That's never going to be as much resolution of data as you will get with wires. But even so, they were able to show that they can very crudely pick out what the person is seeing. Let me show you a video clip. On the left is the image the person, or the video clip the person was watching, and the brain scanner couldn't see that, could just see the activity in their brain, and the right is its closest pick from its own library of videos, of what video it thinks most resembles the one that the person is watching. Okay? So you can see it's very far from perfect, but the algorithm, just by looking at the brain data, has some vague idea of what it is this person is looking at.
Is there a training process involved in this?
There is for the computer, not for the human.
Yeah.
Yeah, this is a machine learned algorithm.
And
where
it
they've
works
taken-
only with a fixed set of clips, or?
It is using a fixed set of clips, but you can imagine many other ways it could have taken the input of the brain and mapped it straight into. In fact, there's a classic set of experiments where you show someone a very vivid picture of a red triangle, put them in a brain scanner, and you can see kind of a triangle lighting up in their visual cortex. The things are aligned roughly in that direction. Okay, so now we've seen data in, data out, in video, audio, movement. There's other experiments in monkeys where they send touch data in, so an artificial limb will also tell them what they're touching. We can probably, as we can get emotional impulses into that deep brain simulator, we can probably get those out as well. And then a real frontier is, could we translate, could we send back and forth more than just sensory data, more than even emotions, but actual memories, for instance. And the group that was working on the hippocampus implant is now working on bridging the hippocampi of 2 rats together. They want to train one rat to do a maze, and then see if another rat that has never seen the maze, but has its brain wired up to the first rat, can run the maze with the foreknowledge gained from its friend. Which is really just one step away from Keanu here saying, I know Kung Fu. Now, I talked about all the great things you can do with this technology, right? And it is science fiction that's becoming reality. But let's talk about the practicalities and the limits. Who can identify the thing on the right? And if you've seen this example before, don't say. Who has not seen this can tell me what that is on the right?
Lady in a hat.
Lady in a hat, very good, you're right. At Google, I have Jesus was the first answer, the Statue of Liberty was the second, Lady in the Hat was the third. Okay, so this is how Jens Naumann, the blind guy, sees. He has a 16 by 16 grid of pixels, so you see why nobody else was in the parking lot with him. Right? I mean, this is not great vision. It's better than a single black pixel, which is basically what we had before. It's way better than that. You can see obstructions as opposed to non-obstructions, but it's not really that great. The technology is a long way to go. And the primary limit there is actually just the bandwidth. The brain has about 100 billion neurons, about 100 trillion connections between neurons, But the most sophisticated system we've used